This is the modern picture of the brain. And this is the problem. In 1925, the philosopher Bertrand Russell wrote that physical and perceptual space have relations, but they are not identical. And failure to grasp the difference between them is a potent source of confusion, and that remains so today. I'd like to do a group experiment very briefly to try and demonstrate this. If you would all look at one of your fingers, you know that your finger is bombarded with electromagnetic radiation. You also know that some of this radiation bounces off the finger and gets focused on your retina. Now, the retina is particularly sensitive to the radiation between 400 and 700 nanometers. This is what we call visible light. But the retina has another job. It's a transducer. The transducer converts energy from one form to another. So the electromagnetic energy is converted into a blizzard of nerve signals which go rushing down a million fibers of each optic nerve at 1/1,000,000th the speed that they approach the eyeball. And the next thing you know, your finger appears in your perceptual space. You're the percipient, the finger is the percept, and it appears to be stuck on the end of your arm. So we think, if we've been awake through this meeting, that most of the formulation of this percept occurred inside the skull. So is the percept inside the skull or outside the skull? And this is what Bertrand Russell was getting at. It's neither. Because to assign a location inside or outside of the skull is to confine the percept to 3D physical space. And the percept is in non-physical space. And it does not like to be confined to 3 dimensions. But is the percept real? Well, it's not an illusion, which is the confusion of the senses. It's not a hallucination. It's a real percept. Just like your real physical finger is real, except they're different. But they're private. And that's what makes them difficult to study. And so, as you've been listening about, we tend to have people who look at neural correlates or dynamical correlates or quantum correlates. I'm going to cover a little bit about dynamical correlates, and we're going to talk briefly about fractals, which underlie nonlinear dynamics, different dimensions, attractors, which causes folk a lot of confusion, and look at the emergence of consciousness from anesthesia during evolution, from sleep, and look briefly at Gestalt and multitasking, and also explain why we sometimes use very high sampling rates when we're measuring EEGs. You put a triangle on a triangle on a triangle, and you form a Koch snowflake. The triangles you add are self-similar. The snowflake, if you unwrap its perimeter, forms a Koch curve, which is too wiggly to be a one-dimensional line. It doesn't cover enough real estate to be 2 dimensions. So the dimension of that line is log 4 over log 3. It's 1.26. It's a fraction of a dimension. That's why it's called a fractal. Fractals appear throughout nature, and they also are very important in dynamics. They also occurred a long time before mathematicians were around. So here is a Koch curve in an ammonite shell, which was dug up as a fossil about 8 miles from where I live. This is a cone within a cone within a cone, a Romanesque cauliflower. Now, you say, well, why does nature need all those fractals? It is an incredible way of compactifying natural living objects. It means that by the way that the tubes spread out, for example, your bronchi, you can move massive amounts of air at a very, very low pressure. So they lend for very, very high efficiency. neurons are fractal. These are Purkinje cells showing the fractal branching. Now here are two EEGs from the same subject. The red one is 100 milliseconds long, and it's the EEG of a burst of volition, when the person suddenly decided they want to hit the buzzer. The black one is the relaxed EEG of someone who's blindfolded, and it's 1 second long. So the black one is 10 times as long as the red one in real life, but very similar. Now, I'd like to make a little bit of analogy here. Supposing that wiggly bit of string is an EEG. An EEG is really a one-dimensional extraction from what's going on in the brain. So what's the ball of twine doing there? That is the attractor. If you ask yourself, why is that bit of EEG there? Why is that curved and not a pointed sawtooth or a square wave? Well, that is the way that is, because that is the way it was in there. It's the attractor which actually causes the shape of the EEG. Not only that, if you take the twine, which you will notice has a memory of its previous shape, you can gently push the twine back into the ball of string and reconstruct the attractor from which it came. And that is what we have been doing. We have a little computer software which reconstructs the attractor from the EEG. We started doing this under anesthesia, and I would point out, in the 80s, Watt and Hameroff were doing a similar sort of thing. Then he got sidetracked. Now, let's look at this attractor business, because people get confused about this. This is a classical picture from Scientific American when they started writing about chaos theory in the mid-80s. Take a simple pendulum, plot the velocity versus position. That circle is drawn by a dimensionless point, which goes round and round, tick-tock, tick-tock, tick-tock. It doesn't have any size, but it has shape. If you perturb that clock, you get a wobble on that point, but the point is rapidly pulled back into line by the force of the circle, which is the attractor. Now what the attractor actually is the signature, fingerprint, hieroglyph, whatever you like, of the dynamics that are going on at the time. Every time this point moves a bit, there's a fluctuation in the balance of forces that are affecting that pendulum. Now, this is a mechanical advantage, mechanical example, and of course, we can have EEG examples too, because it works exactly the same way for electricity. So here is the previous one-dimensional limit cycle attractor with a sort of sine wave. You won't see that much in a human unless they're having an epileptic fit. But now we look at the isoelectric EEG with a burst. Now, notice the fractal pattern of these lines as they curl in towards the middle. So that is a 1.5 dimension fractal attractor. And it tells us something about the EEG that we can't tell by looking at the one-dimensional squiggle on the paper. If we then have two waveforms coming along, they can be combined in this periodic attractor. Now, notice that they are bound together. This one-dimensional point describes both incoming nerve impulses. It's bound as a zero-dimensional point. If a third one comes in, then you can get a torus attractor. Now, the brain is a dissipative organ. In a dissipative system, if you go from point to periodic to torus attractor, as the system warms up, that is one of the classic pathways towards chaos. And here are the real deals. This is what Hicks and I described a few years ago. We described the dynamical stages of anesthesia rather than the clinical stages. So this is stage 4, which we don't often see. We occasionally make people very deep if we're doing certain brain operations. That is basically isoelectric with a burst. Here is stage 3, periodic attractor. That is your 1.5 dimensional periodic attractor. Here is the torus attractor, which you see right before they wake up. And that is what in the old days was called the stage of delirium, when you're kind of out of it, but kind of going in and out at the same time. And here's our return of consciousness, which is chaotic. The point now is moving freely in a three-dimensional space. Now, chaos, you remember, is aperiodic, it's deterministic, and it's extremely sensitive to initial conditions. This is the plot of a patient waking up from anesthesia. The little red dots are the dimensions, EEG dimensions measured every 3 seconds. The orange bars represent the decreasing level of anesthetic. Notice that as the anesthetic decreases fairly smoothly, there is a sudden, dramatic, nonlinear increase from about 1.5 dimensions to 2.5 dimensions, where the EEG changes from periodic to toroidal. And then at about 3 dimensions, the patient wakes up. We couldn't keep a very long trace of this because when they do wake up, they're untrained subjects. They tend to wriggle around a bit and you get a messy EEG. Now, the other thing that happens when you wake up from anesthesia is you see a progressive increase in gamma power. These are log-log plots. So here's stage 3, stage 2, stage 1. And so those increases are very, very significant. So far we've seen, as we regain consciousness from anesthesia, that we've attained an attractive dimension of 3 and that we have increased our gamma power significantly. Now we looked at animals. These are all 1-second traces, Aplysia, Thornback Ray, and human. The obvious difference between these invertebrate, fish, and human is there's a whole lot more stuff in the human's EEG. There's a higher frequency, and the more waveforms in it mean there's more information being carried. Well, that's all very well to know that, and we can study the frequency and so on, but it doesn't tell us about the complexity of the EEG, which you really want to do by measuring the attractor and looking at the attractor, and we have been measuring the attractive dimensions. And what we did was to take as many animals as we could and use them as surrogates for their long-gone ancestors. The reason being that if you take, for example, a fossil frog, the fossil frog's brain looks exactly the same as a modern frog's brain. You can even get an endocast of the brain itself if it was deposited in the right conditions. So we said, well, let's plot the frog's attractive dimension against the time when the froggy first appeared, about 350 million years ago. Do it to as many animals as we can. See what happens to those dimensions through evolutionary time. Now, we chose the best ones, and when I say best, it wasn't just the highest number, but some of the higher ones had EMG, contamination, and so on. But I think the main points from this, and I wouldn't claim any super accuracy for this. Remember, these are dimensional estimates. They're not dimensional measurements so much. First of all, there's an obvious increase in the dimensions, about 1 dimension every 200 million years. Second, the animals more or less retain their evolutionary ranking. Third, we were interested to see who cropped up at 3 dimensions, because that's when our patient woke up from anesthesia, and it looks like the amphibians. So we would say from this tentatively that it looks like the amphibians have enough neural processing power or enough neural complexity to have at least a froggy-type consciousness, maybe. We can say, but I think a little bit more certainly, and this is one of the few places that I would probably disagree with Stuart. There is a theorem in nonlinear dynamics called Poincaré-Bendixson theorem, and basically what it says, if you've got a really simple system, like the pendulum clock, and you've got a really low attractive dimension, like 1, 1.5, that cannot possibly represent anything terribly complicated. So on those grounds, the most dynamical grounds, we would probably claim that the clam and downwards are probably not conscious. The fish are in a kind of limbo land. We wouldn't like to say yay or nay about them. And funnily enough, this actually has some practical implications. Because in England, for example, fox hunting has been banned because it's cruel. There is a move afoot to ban fishing, angling, on the grounds that it's cruel to the fish. It's very interesting that fox hunting is enjoyed by people with a lot of money, and so that was banned. Fishing is enjoyed by a lot of people with very little money, as well as those with a lot, and that was not touched. So the politicians really know which side their toast is buttered. What we thought we'd also do was to look at all our results, not just the big ones. So we now have 290 readings from a whole collection of animals, and we see more or less the same thing, but we see this sort of drizzling effect all the way down to about 1. And what this tells us is that, look, okay, the animal's brain gets more complicated during evolution. The attractive dimension increases. What this tells me is, but he doesn't work in 5th gear the whole time. He doesn't work in 5 dimensions the whole time. Half the time, he just sort of ho-humming and looking at the ceiling and listening to a boring lecture or something, and maybe he's in 2.5 dimensions. So I think what this shows is the variability which has increased in evolutionary time. We tried to look a little bit at sleep, and funnily enough, this was one of the hardest things we did. I, in my innocence, thought, now look, really the very, very best way to investigate consciousness when you want a really good control is to measure someone waking up from a natural, drug-free sleep without an alarm clock, without being prodded with a pencil. And that's not that easy to do. And then when they do wake up, you've got to say, oh, God, when did they wake up? Because they won't say, I woke up. And then, of course, you've got all the muscle artifacts and so on. Anyway, this is the best we could do, and we reckon that this my wife actually, woke up at 18 seconds, 18.5 seconds. Now notice that we're recording at 8,000 samples a second. So this is at least 3 times as fast as your average clinical EEG machine. The first thing we can do is we can split the frequencies up. So we get a nice sort of alpha drop-off at about the time that she woke up, and we get a kind of a bursting pickup in the red beta waves. And because we were downloading fast, we could do rapid serial estimates of the attractive dimension because we had enough data points. So we're measuring the attractive dimension now every 250 milliseconds, and there is an increase in the attractive dimension, but I would not call that significant, not statistically significant. I mean, it goes up a little bit, but nothing to get excited about. This is a bit more dramatic. The 3 seconds before waking up, there's this very strong alpha peak here, and the 3 seconds after waking up, the alpha peak is gone, and there's a little beta peak there. Now, I think what I would say is that we have the software to do very rapid EEG sampling. And I would love for someone else to do this properly, who has a proper sleep lab, EEG machines, or EEG technicians and all the rest of it. Because I think this is a very fertile area for research, which frankly I don't have the facilities for. Now, we did a couple of studies on multitasking. We took a subject and blindfolded her, just told her to sit there and relax, and then picked out some good bits of EEG and measured the correlation dimension. And what you can see is that the brain wanders around from about 2 to 4 dimensions as they think about different things. Take the blindfold off, dimension goes up by 1. Now we multitask her up here. We get her to tap a foot every half second. listen to very loud disco music, and read Plato's Republic, the bit about the cave. And now the brain becomes focused at this higher dimension. And none of this is surprising. It's more or less exactly what we're expecting. We see the same sort of thing in multisensory studies. Now, multisensory studies, they kind of overlap multitasking a little bit. But in the black, we have, again, the blindfold subject, strong alpha, big drop-off in the gamma waves. Now, the subject reads the same Plato again, listens to the weather radio, which is like a continuous drone, smells acetone, and tastes citric acid crystals. So there's at least 4 incoming data streams. And this gets a very brisk gamma response here, and an increase in the dimension, which I would suggest probably is significant. One of the reasons that we started measuring EEGs rapidly because we wanted to get pretty attractors. One occasion, I was sort of doing a volition experiment, and what we did is we did the frontal EEG, the cortical EEG, control EMG, and then the bottom line is the strobe. The subject was told to sit there, relax, hit the button, and as soon as he saw the button, to pout. We find pouting is much better than blinking because it doesn't send any muscle stuff up to the forehead. Plus, you've got you've got short nerves and a minimum amount of transit time. And again, when we look back, here's the pout, which is nice to see because it means that we can say pretty certainly that there was not a lot of muscle activity here. Here's the flash, here's the pout, and between the blue and the red line, we saw again and again this what we call a gamma burst. They were between 80 to 120 milliseconds long. But the point about this gamma burst is only 100 milliseconds long. If I was measuring that EEG at 240 samples a second, I get 24 data points, with which I could do virtually nothing. At 8,000 samples a second, I get 800 data points. So now I can get a nice high-definition view of the burst. We can see that its most powerful frequency is 86 hertz, and we get a very nice dimensional estimate of about 2, which is what the attractor looked like. So let's just sum up where we're at. We basically subscribe to Walter Freeman's theories of consciousness. And he studied animal brains for about 5 decades now, I think. But I'm going to try and give you a potted version, and then we add a couple of little things on the end. Memory stored as synaptic configuration. Repeated exposure, say to an odorant, will solidify that configuration in a Hebbian way, that is, neurons that fire together, wire together. When the animal smells a smell, it's not one little bit of the olfactory cortex that fires off. The whole cortex fires off. It's like an orchestra. And for each smell, the orchestra plays a different tune. So it's as if the music itself was the variation in synaptic configuration. This sends a gamma burst from the olfactory area to the various sensory parts of the brain. This is an AM spatial pattern. This is amplitude modulated. And in the forebrain, somehow these different senses come together as a gestalt or a combined sensory experience. Now, he has very good evidence to show that this process is cinematographic. That is to say, that the information comes in to the sensory areas of the brain in a cinematographic way, like shots on a movie film, I'm not going to say exactly how big they are, but let's say for the sake of argument, they come in at 40 hertz and they're 25 milliseconds a frame. We have shown, I think, that the attractor shows data synthesis vary approximately 1 dimension per sense. That little moving point, the dimensionless point, can easily draw, if you like, two things at once, so long as each of the things has its own dimension. The synchrony, obviously there's local synchrony or we wouldn't get an EEG at all, and I'm not going to go into overall synchrony because the way we did our measurements, we can't even do that. We then have to ask ourselves, from what we've found out, where do we stand on the problem of dualism? And how does the three-dimensional brain perceive five-dimensional dynamics? The way that Walter describes it, if I get this right, is that the resting brain, suppose the brain just before you wake up, is in a low-dimensional chaotic state. And he says this is the best way to be because it's analogous to soldiers parading around a town when they're defending it rather than being asleep in the barracks. If they're marching around the town, something happens, they're instantly available. So this slow, kind of low-dimensional chaotic system is going on. Then the sun rises and a shaft of light comes through the curtains. The AM wave packet joins that chaotic mess and gets incorporated into it. So that when it's thoroughly mixed, the sensory input becomes part of the mind rather than an object perceived by the mind. Now, I'm not getting into what is the difference between the mind and consciousness. I'm talking about every day, the man in the street mind. So it becomes incorporated into the mind, not perceived by the mind. So in that regard, we're not dualists. However, we would not say that the mind and the brain are the same thing. Because to us, that doesn't make any sense. Unless, I guess, after this meeting, unless you're getting way, way down to Planck level and that sort of stuff. I'm talking about the physiology lab. Now, how does the three-dimensional brain cope with five-dimensional dynamics? We'll use the dimensional analogy of Mr. Square in Flatland. Mr. Square, you remember, is a two-dimensional creature in a two-dimensional world. A sphere comes to visit the perfect three-dimensional object. The square can't even see it. The square might see one point where the sphere touches Flatland. How is the dimensionally impaired square going to perceive a higher dimensional object than himself? If this sphere passes through the fabric of Flatland and leaves a hole, the square can see it. As the sphere passes through, the hole gets bigger and bigger, bigger, smaller, smaller, smaller. If the square can remember that first little round thing as the others are accumulating, and he can stack them together, then he can stack them together in a shape which resembles the original shape of the object. So he now has moved from being a dimensionally impaired shape to a shape who can perceive an object at a higher dimension than himself. And we call this the honey spoon principle because I use a honey spoon for the photograph. We wondered how big that honey spoon was. That is, how long that conscious moment was. So now we took full advantage of our software, and we were measuring now at 40,000 samples a second. And we had the subject doing mental arithmetic. Now, the brain is working very hard doing mental arithmetic, but we would not expect a very, very high dimension because it's focused on one job. If it were working hard and doing lots of different jobs, then you expect a higher dimension. So this is the frontal EEG of a subject subtracting 3s or whatever, 14s from 500 between 3 seconds and 3.5 seconds. And what we did was we said, okay, let's look at the first 25 milliseconds. Well, all you see is a couple of sine waves. And we know from experience that a couple of sine waves are going to give you a circle, and that dimension is going to be about 1. So they said, okay, well, let's keep adding. Let's go 0 to 25 milliseconds, 0 to 50 milliseconds, 0 to 100 milliseconds. Keep adding the data until the dimension flattens out. And at that point, we could maybe reasonably say, okay, well, it's taken that long for the dimension, the attractor to mature. Maybe that conscious moment is that long too. And this is what we found. This is the same EEG. And it levels out at around about 400 milliseconds. Notice it's not terribly high. It's about, just over 2. But this is highly focused brain work. Well, then we wondered, well, it took 400 milliseconds for someone who was concentrating to get that attractor. What about someone who's multitasking? Would that just take the curve way out here somewhere? Or would that elevate the whole curve up a notch or two? And it did that. The points are farther apart because we took an old trace and we weren't sampling so rapidly. So I would say, in summary, with our honey spoon theory, we think that successive frames of AM, or amplitude modulated, wave packets are added to the front of this thing about every 25 milliseconds. This thing is around about 400 milliseconds long, and then, of course, the tail end of it fades away like a comet. The signal just fades away after that time. So it's fading at the back. It's being continually refreshed at the front. And the honey spoon now provides a location for consciousness, although I haven't tried to say exactly where the real honey spoon is. It frees the percipient from the constraint imposed by the event horizon of 3D physical space. Now that gets neatly around all the arguments except the central argument. The attractors that we see are only a representation of the forces in action. So exactly what those forces are and where they are and at what level they are, we don't know. Thank you very much.
I would like to know that these studies that you have done is also extended to the invertebrates like insects?
I know what you're going to ask. How do you do an EEG on a crayfish? Yes. The only way we could get permission to do the animal studies, the hospital institutional review board wouldn't touch it with a 20-foot pole. They said, get out of here. You must be joking. So then, because I live on a farm, I got permission from our local county extension agent, which is a combined government and university job. And she said, yeah, you can do that, but you mustn't harm the animals, and then you've got to set them free afterwards. That's why we could not do the kind of EEGs that neuroscience and nature want, where you've got to put 6 animals in a cage, keep them at the right temperature, put burr holes in their head, and so on and so forth. In answer to the question, with an invertebrate, the brain goes around the pharynx. So you just pop a little soft probe into the mouth. The probe I used for crayfish was the floppy end of an arterial line wire. When you put a wire into an artery to put a catheter over it, the end's floppy, so you don't put it through the back wall of the...
Should we also consider this as a parameter to study the evolution of consciousness?
I don't see why not. I mean, I did it out of interest more than anything. I would warn you that quadrupeds are very, very difficult to do EEGs on because they got all this muscle on the top of their head that holds their head up. The worst of all is the possum, which has a muscle about that thick. And you have to look a long way before you can get a bit of EEG that you think is half decent.
Thank you. Thank you. Fine.
Thank you.